Welcome. In this presentation I will continue to discuss different methods to measure gas emission. Techniques using tracer gas release as well as a method to derive emission factors will be shown, and examples will be given from landfills and ship emissions. In my previous presentation about measurement of gas emissions, I gave some example using mobile column techniques and showed some applications from volcanoes, megacities and industry. In the following, another approach using tracer gas will be discussed. In this method, a tracer gas is released in the source region with known emission rate. Assuming that the tracer gas is diluted in the same way as the gas under study, the emission may be determined from the ratio between concentrations of the two gases measured in the recipient region. An application where this method has been applied is methane emission from landfills. Methane is a very strong climate gas, and thus there is a need to quantify and, if possible, reduce its emissions. In old landfills, organic material has been deposited and then covered with soil or clay. The anaerobic conditions in these deposits produce methane gas, which eventually reach the surface. These emissions are distributed over large areas and may be concentrated to cracks or other weaknesses in the cover material. Thus, these emissions are difficult to quantify. The method chosen here is based on releasing a tracer gas at the landfill with well-known release rate. The researchers then went down in the landfill far enough to ensure a good mixing of the tracer gas and the methane emissions from the landfill. In this example, they used nitrous oxide as tracer gas and used a multipath Fourier transform infrared instrument to analyze the gas a few kilometers downwind the landfill. Simultaneous measurements of the concentrations of methane and nitrous oxide was made with high time resolution. The ratio between these concentrations was determined with linear regression analysis, and as the emission rate of nitrous oxide was known, the emission rate of methane could be determined by scaling. In the example, the emission rate of methane was determined to about 300 kilograms per hour. Our final example will be quantification of the sulfur content in ship emissions. It has been estimated that sulfate aerosols originating from combustion of coal and oil with high sulfur content are responsible for about 30,000 deaths per year in Europe, due to complications of various illnesses. As ship traffic has been recognized as the major source of these emissions, EU has implemented so-called sulfur control areas, where only low sulfur fuel is allowed. Thus, there is a need to be able to monitor the compliance of these regulations. One method by which the sulfur content of the fuel used by a ship can be determined is the Sniffer method. In this method, an airplane is flying through the exhaust plume from a ship while it is simultaneously measuring carbon dioxide and sulfur dioxide. As carbon dioxide represents the carbon content of the fuel, while sulfur dioxide represents the sulfur content, the ratio between carbon dioxide and sulfur dioxide multiplied with a conversion factor yields the sulfur content of the fuel. Thus, statistics of the compliance to the sulfur fuel regulations can be obtained. It is also possible to track individual ships for further legal actions. A more effective way to gather statistics from a large number of ships is to use a stationary sniffer system. Here the ratio of carbon dioxide and sulfur dioxide is measured from a fixed location that is frequently encountered by the plume of passing ships. Thank you for listening. I hope you have enjoyed also this presentation about measurement of gases emissions and emission factors.